Okay, so today what I want to cover is a really major topic in logic, and one of the reasons that logic is useful, if you like, and that's that it provides, as we discussed already in the second lecture, at an informal level, logic provides mechanisms for modeling human reasoning using logical formulas in a precise way. And it does that by providing what are called proof systems. Proof systems, or sometimes inference systems. And what these are, they give us precise mathematical rules for reasoning with formulas. So let's say proof systems for reasoning with formulas. Logical formulas. And with these precise mathematical rules, we can capture the full power of human reasoning about when we reason with logic. And as humans, when we reason, we're essentially, especially when we reason mathematically, we're reasoning with logic. And so we're going to see one of these proof systems today, but before going to the proof system we're going to use, I just want to say a little bit about different styles of proof systems that one might consider, because there are many, many ways of doing this. So let's put it here. There are two main styles of proof system that one might consider. Now, the first style has some advantages. Well, both styles have some advantages, but the first style is proof systems. So we encode rules of logic. We're going to give precise rules for the rules of human reasoning. And in the first style, we're going to have systems that allow us to model in quite a faithful way the natural process of human reasoning. So if you come up with a nice informal mathematical argument, then the logic of that argument will be modeled rather faithfully. It will be possible to encode that natural style of argument rather naturally into these proof systems. So proof systems that model natural styles of reasoning. And the other style is systems that, like the style of reasoning that the proof system is going to give us some formal rules for reasoning with formulas. We're going to say, okay, well, we've got this formula, we're assuming that's true, and we've got this formula that's true, and from those formulas, we can deduce this formula as being true. And there are going to be those proof systems that don't follow natural styles of reasoning in that, but rather unnatural styles of reasoning. Systems with unnatural styles of reasoning. Unnatural, and let's say, and complex styles of reasoning. That's two words here, styles of. Let me put a space in. So systems that model natural styles of reasoning, these have names. So two important ones are natural deduction, called natural deduction because it models natural human process of deduction, logical inference. And another one is sequent calculus, also known as Gensen's sequent calculus. Gensen, after Gerhard Gensen, who introduced it. actually he introduced natural deduction as well, and he introduced both styles of proof system in the same paper. So this was a very, I think it was in 1935 or 1936. It was a very important paper in logic. So he introduced natural deduction and sequent calculus. So those are examples of systems that model natural styles of reasoning, and the main style of systems that one might consider a very important style of system with an unnatural and complex style of reasoning is what's called Hilbert systems, after David Hilbert, the very famous German mathematician. So if we want to mark pluses and minus, good points and bad points, well, modeling a natural style of reasoning seems a very good point, whereas having complex and unnatural styles of reasoning seems a very bad point. So let's mark that as a minus. So one might be tempted to go in this direction and consider natural deduction or dense and sequent calculus. And in fact, in previous incarnations of the course, I've always started with Genson's sequent calculus. But there's a big disadvantage to that. And the disadvantages of these of the systems that model natural styles of reasoning is that actually defining the rules for reasoning themselves is rather complicated. So these systems are complicated to define. They're rather beautiful, so it's actually worth taking the effort. But still, they are complicated to define from a mathematical point of view. So that's a minus. Whereas the Hilbert systems are very simple to define. So that's a big plus. So as I say, in previous incarnations of the course, I've started with sequent calculus. But doing that, we need a whole lecture, a whole week, just to introduce the sequent calculus proof system, and then another week after that to prove the important properties of it, especially the soundness and, in particular, the completeness result, which is a major result about the proof system. So with this, it would take us 2 weeks to go through proof systems. This year, I've decided I want to not spend so long on this material. So instead, I'm going to introduce a system, the Hilbert system, because it's very simple to define, in spite of its disadvantages that it supports an unnatural and complex style of reasoning that we'll see. And then later on in the course, once we've gone through the main material, including Gödel's incompleteness theorems, I may, in the last lectures, come back to proof systems, and we may have a look at Genson sequent calculus at that point. Okay. Right, so we're going to, so the main topic today is a Hilbert-style proof system, or Hilbert system for short. So let me just call it a Hilbert system. And so as I've said, the main advantage is that it's very simple to define. And I want to keep the definitions as absolutely simple as, at least as I know how to do. So let's say as simple as possible, though something simpler might in theory be possible. And in order to do that, I'm going to apply Occam's razor, which is to reduce what I'm presenting to the very bare minimum. And to do that conveniently, to give as simple as possible, as simple and concise as possible the definition, I'm going to just have a very limited logical language. So for convenience, let's use the blue pen. Convenience, we're going to restrict logic, restrict formulas to. So remember in the third lecture, I think, we did fragments of logic that are sufficient for expressing all of logic. And one particular fragment was to combine negation with implication and either of the quantifiers. And we're going to essentially have negation. We're only going to give ourselves in our vocabulary for building formulas, negation, implication, and the universal quantifier. But in fact, to get negation, it's going to be convenient for me to have the false symbol around, the false logical constant, or falsum as it's called. So I'm going to restrict to falsum, implication, and universal quantification. Where's negation gone? Well, negation is defined as A implies false. Okay, define A, not A, to be an abbreviation for A implies false. Okay, so obviously this is well, let me just write it. This is a sufficient fragment, sufficient collection of connectives by lecture 2. So all first order properties can be expressed just using combinations of false, implies, and universal quantifier. So once you've got negation, you can define existential quantifier as not for all not, and all this kind of stuff that we did in lecture 2. So now, without further ado, I'm just going to go and present the proof system. And it's a very simple idea, and I'm going to write the definition on the board of a proof a little bit later. But the very simple idea is a proof is simply going to be a sequence of formulas that we're going to say, well, we prove this formula, prove this formula, prove this formula, this formula follows from those. And so it's going to be a sequence of steps where each step is a formula leading to the conclusion, the last formula in the sequence, which is the thing you're trying to prove. And each step must be justified. And to be justified, it either wants to be an instance of an axiom. So axioms are going to be basic formulas we assume to be true, or it must be justified as the conclusion of a legitimate inference that we can perform. We're going to have a fixed number of rules for these inferences, the conclusion of a legitimate inference from formulas we've previously derived. So we've already derived this formula and that formula, and we have a rule that says if we've got this formula and that formula, then this other formula follows as a logical consequence. So the proof system is going to have two main components, axioms and inference rules. So let's move the camera, and it's sufficiently simple that it's all going to fit on the other board. Whereas if we were doing sequent calculus, well, it could probably squeeze it onto the other board, but there's a lot of machinery with sequent calculus that needs to be introduced that we don't need because we're going to have a Hilbert system. So as you know from the old Greek idea of the axiomatic method in mathematics, an axiom is supposed to be something that's self-evidently true. That's the philosophical idea of an axiom. In our case, axioms are playing they are going to be rather obviously true, but they're playing somehow a different role. It's not the self-evidence that's important. What's important is that we identify a number of formula types that we call axioms, and a number of inference rules that we use to derive one formula from another. And the important thing is that in doing so, we're going to have sufficiently many axioms and sufficiently many inference rules that any valid deduction can be made. So whenever something is a logical consequence of some other formulas, we will be able to prove it using our axioms and inference rules. We need to have identify sufficiently many axioms and sufficiently many inference rules that the proof system is going to work. So we have 7 axioms. in order to do this. So I'm going to say, I'm going to use the proper word for them. They're not actually individual axioms, they're axiom schemas, or schemata is another. The word schema in English has two plurals, the old-fashioned one, schemata, and the modern one that we turned it into a word that you just pluralize with the S. And I'll tell you what schema means in this context in a moment. Let's just write them down. The first one is that A implies B implies A. Now, a little comment to make on this. When I write an iterated implication, the implicit bracketing is to the right. This is very important with implication. Okay, so one says the jargon for this is that implication associates to the right. So I'll leave the green brackets there, but I'm not going to put the brackets in future. Let me say straight away what I mean by this is an axiom schema. So A and B are kind of, well, then what one called a meta variable for a formula or a meta formula. So when I state this axiom, it's actually infinitely many axioms, one axiom for every instantiation of A and B as a specific formula. So an example of an instantiation of this would be, say, X equals X implies Z equals W implies, sorry, that's X equals Y, I said it wrong, implies, well, let's put a quantifier in just to, because there are arbitrary formulas here. So there exists a WZ equals W implies X equals Y. You can instantiate A as any formula, it doesn't need to be a sentence, it can have three variables, B as any formula, and yeah, that gives you the pattern. So it's infinitely many axioms expressed as one axiom schema. Okay, so that's the first one. The second one is A implies B implies C, implies A implies B, implies A implies C. And I'm only putting the minimum number of brackets in that are necessary. The third one is we have, but not B implies not A, then A implies B. So remember, not B is shorthand for B implies false. So these are all the axioms that involve just the propositional connectives. We're going to have two axioms that involve quantifier, the universal quantifier. Let me just check which order I've got them in. So the first one is that if we proved that for all, well, we have the implication that if for all x A holds, then A holds T with any term T substituted for X. So that's very intuitive because if A holds for all X, then A should hold for any specific instantiated in T. Notice the bracketing here is again implicit. If I don't explicitly say that a quantifier extends over a larger formula, it's kind of finds as tightly as possible. So again, the green brackets here are implicit ones. Another axiom says that if we have an implication from for all x, A implies B to A implies for all x B, in the case that this is going to work, so clearly this doesn't make sense in the case that A contains a free occurrence of the variable x. So we have a restriction here. If x does not belong to the free variables of A. And the last two axioms are about equality. First one says that for any term T, so this is again a schema, it's one for each term T. So you can always prove T equals T, it's very intuitive. And the last one, for any terms t and u, we have an axiom that t implies u. Sorry, if t equals u, then if a holds for t substituted for some variable x, then a holds for u. Substituted for that variable x. So very intuitive. If t equals u and a holds for t, then a holds for u, because they're the same thing. And those are all the axioms. Axiom schemas. And we're going to have two inference rules. And the inference will simply say, if we have already derived something in our proof, then we can derive something else as a conclusion from those. And we write the inference rules in the following form. So the inference, we're going to write it premises, a line, and conclusion. So premises is some number of formulas that we write above the line, and the conclusion is going to be a single formula that we write below the line. And the idea of such an inference rule is, if we have already in our proof all the premises, then we can extend the proof by adding the conclusion of the inference rule to the proof. So we're going to see an example of how the proofs are carried out in a moment. But let me just give the two inference rules. So the first one, well, they're both very famous inference rules. This one is particularly famous. But if we had proved, if we've derived A implies B is true, and we've derived that A is true, well then, if A and A implies B are true, then of course you expect B to be true, so that should be a sound inference. And this, we'll use NP for this, because in English we tend to use the Latin name for this, modus ponens. So it's clearly a sound inference. And the second one looks more surprising. That's if we have proved A, then we can prove that we conclude that A holds for all x under a certain circumstance. So provided so it looks a bit preposterous at first. We proved that A holds for some x with some formula A that has an x in it, and we're concluding that for all x A holds. That seems like we're making a massive generalization from A holding for just the x. In fact, we are making a generalization, so this rule is called gen, for generalization. Let me put the proviso below, the generalization. But there's going to be a proviso on this rule, a condition. The proviso is we can only do this in the case that the variable x does not occur free in any assumptions we've made in the proof. I'll tell you what an assumption is a bit later. So x is not free in any assumption in the proof. So I will give you the definition of this a little bit later, but beforehand, just so that you know where we're heading, I want to give you the intuition. And the intuition is, if we've derived that A is true, and x does not occur free in any assumption in the proof, what that means is we've shown that A holds for x in a case in which we've not made any assumptions about the variable x. So we've proved independently of any assumptions about, we haven't made any assumptions about the variable x, we've proved that A holds for x. And because of that, we've proved essentially that A holds for a generic x, so to speak. It holds for an x about which we've made no assumptions. And therefore, X could have been anything and A holds for it. So it's reasonable to conclude that for all X, A. That's the idea. It will become precise a little bit later. And this is essentially the whole proof system. I shall clarify the notion of assumption a little bit down the line. It's not very difficult. But beforehand, let's have a look at some proofs using the proof system. I don't want to spend very long on this, but we're going to give a couple of proofs, and we're going to see from that. When I was talking about the different styles of proof systems, I said the proof system, the Hilbert systems have the advantage that they're simple to define. We've already done most of the work. I hope you agree this is simple enough. If you saw the definitions of natural deduction or secret calculus, you would definitely agree that this is simple by comparison with the definitions of natural deduction and secret calculus. So it's definitely the simplest style of definition. So we've done that. The disadvantage was that these are systems with unnatural and complex styles of reasoning, and we're now going to see this aspect of it because I'm going to give a couple of proofs, and we're going to see that these proofs are a bit awkward, especially since we're proving incredibly simple things. But anyway, one only needs to prove a certain number of very simple things, and then once one's done that, one has enough to get going with, so to speak. So let's clear the board. So the first example I'm going to give is a proof involving both a combination of propositional logic, quantifiers, and equality. I mean, our axioms divide into essentially three parts: the propositional logic part, the quantifiers part, and the equality part. And I'm going to combine them all to show that one of the expected properties of equality holds. So in fact, it follows from these axioms and these inference rules that you can prove that equality is an equivalence relation in the logic. So the three axioms stating that equality is an equivalence relation hold. I'm going to prove, so remember, an equivalence relation is reflexivity, symmetry, and transitivity. I'm going to prove the axiom, well, the sentence that says that equality is a symmetric relation. So that's something very simple. So example proof of the sentence: for all x, for all y, x equals y implies y equals x. And we're going to see that even proving something simple like this, which should not be a difficult thing to prove in logic, is a bit complicated. So what is the proof going to be? Well, I already told you informally. I'm going to again give you examples before I get to definition, that a proof is going to be a sequence of steps, each one of which, for the moment, needs to be either an instance of one of the axioms. The axioms are schemas, we instantiate it with a particular formula, or we're going to use an inference rule to derive the next formula from formulas that occurred previously. So in this case, we're going to start with an instance of one of the axioms. In fact, one has to start with an instance of one of the axioms. If we don't have any assumptions, I'll talk about assumptions later. So here, the instance of one of the axioms is x equals y, implies x equals x, implies y equals x. Right. Now, which axiom is this an instance of? It's not the first one. So, sorry?
The seventh one.
It's the seventh one. Yeah, so you might be tempted to think it's the first one because x equals y and y equals x are basically the same thing. So it looks like A implies B implies A. Only, of course, those are only the same thing because we think of equality as a symmetric relation and we're actually trying to prove symmetry. So to instantiate the axiom, you can only instantiate this with exactly the same literal formula for A in both cases. So it's indeed not the first axiom, but it's the seventh axiom. So the seventh axiom says if we've got for any two terms, t and u, so here t is x and u is y, if A given some formula A, and we're, well, of course, it doesn't matter what we call this variable here. So let's put z here just to make it clear in this case. Doesn't matter what we call the variable here. So if we so this is kind of for any variable z. So if you've got a formula A and we substitute t for a variable, then at the conclusion of the implication we get A and we substitute u for the variable. So here A is the formula. Z equals x. Okay. And here we're substituting it for z for x, but x for z, and here we're substituting y for z. Okay. Right. So now, to get somewhere with this, we want to derive a conclusion from this. So we're going to use an instance of axiom 2, in which this is going to be the A implies B implies C part. So that instance of axiom 2 will give us x equals y, implies x equals x, implies y equals x. That's A implies B implies C, implies A implies C, so A implies B, so x equals y implies x equals x, implies A implies C, so x equals y implies y equals x. This is axiom 2. And now we can apply, remember this is bracketed to the right of these implications, this one and then this one. So this is the left-hand side of an implication, and it matches that. So we can apply modus ponens to 2 and 1, and we get all this right-hand stuff, the right-hand side of the implication. So x equals y implies x equals x, implies x equals y, implies y equals x. So this is, I don't need the implication here. So this is modus ponens applied to 2 and 1. Right. So now I'm going to use an instance of axiom 1, using x equals x for A, x equals y for B. So then axiom 1 gives us x equals x implies x equals y implies x equals x, axiom 1. And then using axiom 6, we have x equals x, with the term t is x. And again, by modus ponens, I can use modus ponens on these two, and I get x equals y implies x equals x. So this is modus ponens on 4 and 5. And now we've managed to derive the left-hand side of this implication, the antecedent, if you like, of this implication. And the succedent on the right-hand side is x equals y implies y equals x. So another application of modus ponens gives us x equals y implies y equals x. And you can see we're nearly there now. And so that was modus ponens on 3 and 6. And now all we need, we don't have any assumptions. Assumptions are formulas that you just stick in the proof for no reason, without any justification. And if you do that, it's an assumption because you're assuming it's true. But we don't need any assumptions for this. We don't want any assumptions because we want to prove that this is outright a valid formula, outright provable. So we simply now, we can do generalization on Y. For instance, generalization and generalization again with the, oops, 9 with X, for all Y. Generalization. Okay, and we're done. I'm not going to do very many of these proofs in the lecture, so I think this example should already be sufficient that you kind of, I mean, you might think maybe you could do it more easily, but I don't think you can. So hopefully you agree with me that proofs in the system are rather complicated. We're proving something very simple, and it involves rather a lot of manipulation involving the axioms. I just want to do one other such thing, and then that will be enough for examples of proofs. One can get a bit of a perverse pleasure from trying to find sort of proofs in this in this Hilbert system. It's really, a bit complicated, but at the end, when you found one, when you've actually managed to get your derivation to work, you do get a kind of, it's like having solved a little puzzle or something. Anyway, so the second example I want to give is I want to prove something very, very simple, which is for any formula A, we can derive that A implies A. So again, something that is a very, very simple logical truth. Now, what's interesting about this is I'm not instantiating A with a particular formula. So I'm going to give, essentially, I'm giving, so whereas here I was deriving a single formula, officially the proof system is for deriving, your proof actually consists of individual formulas, just as we did here. So here we have actual formulas in the proof system. However, sometimes the pattern of the proof will work for any instantiation of the formula. So basically, I'm giving, just like each of these axiom schemas was essentially, this is an infinitely many axioms, one for each instantiation of the formula. What I'm going to give here is essentially infinitely many proofs, one for every instantiation of the formula A. So I'm going to call such a thing a schematic proof. So it's really infinitely many proofs, all follow the same pattern of A implies A. And just out of interest, so let me tell you the proof in natural deduction of A implies A. It's assume A, we've proved A from our assumptions, therefore A implies A, getting rid of that assumption because, so the proof in natural deduction looks like this. You need to understand how natural deduction works, but it's very simple. The proof in Gensen sequent calculus is also extremely short. The Hilbert system proof of this is as follows. I mean, this should be a self-evident truth. One doesn't ever want to reason that A implies A. It's the most natural thing in logic that A implies A. But to prove it in our Hilbert system, well, we first use an instance of axiom 2. We use this one. A implies 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 A. So this is in our A, B, C in axiom 2. This is A, this is B, and this is C. I hope I've written it out right. So this is axiom. This is an instance of axiom 2. Now you can. No, I didn't need these brackets here. I mean, hopefully you can see I've concocted this so it's going to work, because now this is itself an instance of axiom 1, because if I put B is A, A implies A, so as an instance of axiom 1, we have this, A implies A implies A implies A, with appropriate bracketing that's hard to say, hard to include when you say A implies A implies A implies A. So that's axiom 1. And now we see from 2 and 1 by modus ponens, we get A implies A implies A, false implies A implies A. That's from 1 and 2, the modus ponens from 1 and 2. And now, again, we've got an implication, the left-hand side of which is an instance of axiom 1. So we use axiom 1 with A and B the same formula. So axiom 1. And again, by modus ponens, we now, with these two formulas, we get A implies A. So modus ponens from 3 and 4. Right, so that's the kind, yes?
Wouldn't just the steps 4 and 5 be enough to prove this?
Steps 4 and 5.
Yes.
What do you mean steps 4 and 5?
Since, I mean,
Well, so here we've got A implies A implies A.
yes.
So that's okay.
And then
How are we going to get that?
by modus ponens.
Well, we don't have A.
Okay.
Yeah. So there is, in this case, I know for a fact there is not a shorter proof of this. And anyway, I hope you agree it's complicated. So we're not going to do any more proofs. But maybe just before the break, I've just got time to squeeze this in. I want to mention some similar things that one could prove. Oops, I'm pressing the wrong button. I'm going to call this the proposition. So I'm going to give a proposition which are called schematic proofs, which is that similar schematic proofs can be found of all the following schemas. And the point here is, in order to, what we're going to do is prove that our proof system is complete in the sense that I already talked about in lecture 2, that we're going to define properly and formally in this lecture. And the main goal today is to prove that it's complete. So it's in the sense that every logically valid inference, every logically valid consequence can be proved in our proof system. And in order to prove that, one needs to get off the ground by establishing sufficiently many logical truths do actually follow from the proof system. And this proposition now, together with that A implies A is provable and the equivalence relation property, summarizes many of these proofs that we get these logical properties that we're going to need. So the first one says we can prove A implies B implies C. Somehow implications are independent of the order in which one lists the antecedents, if they're nested appropriately. Implication is transitive, so if A implies B and B implies C, then A implies C. Thirdly, the falsity behaves in the way it should, that everything false implies everything. Negation, well, we had the kind of contraposition axiom that if not B implies not A, then A implies B. Of course, in classical logic, not B implies not A is equivalent to A implies B. So we want to have the other implication of that, but that's provable. So A implies B implies not B implies not A. That's provable. To especially emphasize, we've got classical logic. We've had double negation elimination or reductio ad absurdum. So if not A implies A. And lastly, something related, which is also classical, which is if we can prove that not A implies A, then that's enough to establish A. So you can have fun finding your own schematic proofs of all these statements. They're going to be useful later in the lecture. Right, I'll pause here. Okay, so we've seen the proof system and we've seen examples of proofs, and I stated this schematic proposition giving a lot of examples of other things you can, as an exercise, try to prove yourself using the axioms and proof rules of the system. I still haven't given a proper definition of proof, and now it's appropriate to do that. And there's some things that I want to do in the definition that's slightly more general than what we've been doing so far. In that, so far, our examples have been proving formulas outright, and in doing so, we're showing that the formula is logically valid. But more generally in reasoning, we don't just want to establish that formulas are logically valid, but it's useful to establish that some formula follows as a logical consequence of some other formulas that we might be assuming as being true. And our general notion of proof is going to allow us to do this, to prove a formula from a set of other formulas that we're assuming to be true, and we want to explore the consequences of those assumptions. So in general, a proof of a formula A from a set of formulas is a finite sequence of formulas ending in A. We want A to be the conclusion of the proof. Ending in A. So just to use the word conclusion here. This technical word, the last formula in a proof is the conclusion. Such that so the only additional thing to say is that the proof, the sequence of formulas, adheres to the rules for building a proof, so follows the rules for being a proof. So such that every formula in the sequence is one of the following. So there are three different cases. It can either be a formula in gamma, so the point is we're allowing ourselves to prove A from an assumed set of formulas gamma, and so to show that a formula follows from gamma, we can use one of the formulas from gamma in proof. So that's what we're doing here, a formula in gamma, in which case, so that's called the formula B. Every formula B in the sequence is, so if it's a formula from gamma, in which case B is called an assumption. Or an instance of one of the axiom schemas. Or the conclusion, it must be one of these three things, or the conclusion of an inference rule whose premises appear earlier in the proof. And that's it. And we're going to have some notation for this. So far, all our proofs have been proofs from no assumptions, an empty set of assumptions, proofs of just the formula being logically valid, that it's holding outright, but in general, one wants this more general situation. So I'm going to introduce some notation for this. We write gamma turnstile A. So notice we had a similar relation for logical entailment in the second lecture using this symbol. For the relation of what we're going to call derivability that involves the proof system, we use this related notation called the turnstile with just a single horizontal bar. And this means that A is provable from gamma. So this means A is provable from gamma. We also say A is derivable from gamma. This is the derivability relation. Main result of the course is going to be, not of the course, sorry, of today's lecture, is going to be that this derivability relation, being able to prove that a formula A follows from these simple axioms and rules, follows from the assumptions gamma, is exactly the same thing as the logical entailment relation that we had in lecture 2. So that's a very important result, and it's far from obvious that that should be the case. You know, we've got some sort of rather arbitrary axioms and rules, and quite natural that when we can prove something that implies logical consequence or logical entailment, but it's very far from obvious that these two relations, that this relation coincides with the logical consequence relation. So that's going to be our main result. So working towards it, before I even formulate that result, I want to establish a very useful little theorem. It's purely about the proof system, which allows us to show that a formula is a logical consequence of another set of formulas gamma without going through the pain of actually providing the proof ourselves in all the steps. It gives us a sort of shorthand for showing that a proof exists. And the idea here is that, you know, when one's reasoning naturally, in usual informal reasoning, you want to show an implication. A very standard thing to do is you assume the left-hand side of the implication, and you do some reasoning, and you show that the right-hand side is a consequence of the left-hand side, and doing that reasoning is tantamount to establishing an implication. A very important result about our proof system, which to a large extent just is what explains the exact formulation of the axioms, is the following result that says our proof system actually supports the same kind of reasoning implicitly. But this is called the deduction theorem. And this says for any set of formulas gamma and formulas A and B, if we can prove B from assumptions gamma and A, then actually we can prove A implies B from gamma. So the deduction theorem makes it obvious why we can prove A implies A, because obviously we can prove A formula B from assumption A. You don't need to do anything. You just it is an assumption, so you can use A in the proof. And the deduction theorem tells us then we have a proof of A implies B. But of course, in the proof of the deduction theorem, we're going to need to construct these proofs and show that such a proof is constructible in each case. And in that case, we're going to use the proof we had of A implies A. So I do actually want to go through the proof of this. It allows us to bypass actually reasoning with the proofs, fully writing everything out as a proof in the proof system by doing shortcuts like this, by making assumptions if we want to prove an implication. So the proof of the deduction theorem. So let's move the camera. So let this be a proof of B. This is the sequence of formulas appearing in the proof, and the last one is the conclusion B. So B, a proof of B from gamma and A. And we want to show that we can prove from gamma, we can prove A implies B from gamma. So we show, we're going to show this in turn we're going to show in turn for every formula that appears in the proof that we can prove A implies that formula from gamma. So we show for I from 1 to K, from gamma, we can prove A implies BI. And essentially, this is kind of by induction on K, if you like. We prove it for 1, then for 2, then for 3. And so for each I, we can assume it's true for all the Bj strictly less than Bi. So to prove for I, we can assume that gamma proves A implies Bj for every j strictly less than I. So we've already seen that we can prove all the A implies Bj for all the earlier formulas in the sequence, and we want to deal with the next one, which is Bi. And now we want to show that we can prove from gamma A implies Bi. So we're simply going to do a case analysis on the reason that the formula Bi appears in the proof. So we show that we can prove A implies Bi. So what are the different reasons that Bi can appear in the proof? Well, it might appear in the proof because it's an assumption, because it's an axiom, or because it's a conclusion of an inference rule. So in the case that Bi is an axiom, or an assumption from gamma rather than so if it's an assumption, we've got our proof B1 to Bk is a proof from assumption set gamma together with A. So if it's an assumption, it can either be from gamma or it can be the formula A. Okay, so this case covers if it's an axiom or an assumption from gamma. Whoops. So in this case, well, if it's an axiom or an assumption from gamma, then we have also that Bi can be proved from gamma, because we didn't use the assumption A. I mean, it's either an axiom or it's an assumption from gamma, so we immediately have that. And by axiom 1, we have that gamma proves that Bi implies A implies Bi. That's an instance of axiom 1. And so by modus ponens, we have that indeed A implies BI as a consequence of gamma. Okay, that's one case. In the case that BI is an assumption, is the only other assumption it can be, which is the formula A. So if BI is the formula A, then the formula A implies BI is, of course, the formula A implies A. And we already proved that we can prove that, as that was my example proof. So we have that we can prove A implies A without using any of the assumptions in gamma. So clearly A implies A is provable from the assumption in gamma without even using those assumptions. So A implies BI is provable by the example proof of A implies A earlier. Okay, so we've dealt with when BI is an assumption or an axiom in these two, all those cases. So it remains to deal with the case that the two cases in which BI is derived from an inference rule. So if BI is the conclusion of modus ponens, and if it's the conclusion of modus ponens, then for two, so we've got BI somewhere here, for two earlier formulas, we must have a BJ for an earlier J and another BJ prime of the form BJ implies BI. So from BJ and BJ prime of the form BJ implies BI. So then, by the induction hypothesis, but this is the induction hypothesis here, that A implies BJ is provable for every strictly earlier formula in the proof. But by the induction hypothesis, we have that gamma proves A implies BJ, and gamma proves A implies BJ implies BI. And now by axiom 2, we have that an instance of axiom 2 is A implies BJ implies BI, implies A implies BJ, implies A implies BI. And using this, a modus ponens once with this formula, and again with this formula, we get that A implies BI. So by modus ponens twice, and B twice, we have that A implies BI is derivable. And essentially this step is the reason that axiom 2 is a very important axiom here. Anyone's interested in the break, there's a relationship to lambda calculus versus combinatory logic with these axioms, but I don't want to spend time in the lecture on that. So lastly, the last case is that if BI is the conclusion of the other inference rule, so if BI is the conclusion of Gen, so in this case, so BI is of the form for all x bj, the sum bj. So by the induction hypothesis, so bj occurs earlier in the proof. So by the induction hypothesis, we have that A implies bj is provable from assumptions gamma. So by generalization, we have that rule X, A implies Bj is provable from assumptions gamma. And now we look at axiom, whichever number it was, 5. Axiom 5 said that rule X, if we've got an implication here, then we can put the quantifier inside as long as X does not appear free in A. But X does not occur free in A because we were able to do this generalization step in our proof of B, and our proof of B was from assumptions gamma in A, and in order to perform the generalization step, there was this condition that the variable X used in the used to generalize must not appear in any of the assumptions. So X cannot appear free in gamma or in A. So X does not appear in the free variables of A because generalization is used in the proof that rule X Bj followed from the assumptions gamma and A. So this is okay, and now by modus ponens, we again have A implies rule X Bj follows from gamma, is derivable from gamma, i.e. that's indeed A implies Bi. Okay, so a bit of fiddling around with the axioms and the proof rules, but it works, that's the main thing. And it's very useful. And once we've got this, then we can be a bit more relaxed about. Well, we don't need to give all proofs from first principles. We've now got a higher level tool to deal with proofs in the proof system, and this is really useful. Good. So we've done that. So now I'm going to formulate the main result, which is the soundness and completeness of the proof system. We'll dispatch of soundness in the current part, and then completeness, which is really the most substantial proof that we've done in the course so far. Well, we haven't done it yet, but by the end of today, it will be the most substantial proof that we've done in the course so far. I'm going to use the whole of the last hour to prove completeness. And that does not give enough time to do it in full detail, but probably you don't want to see the full detail. Anyway, I'm going to give enough, well, there'll be more details in the notes, but hopefully I'm going to give enough information in the last hour that you'll understand why completeness holds. Right, so that's. So the main theorem, soundness and completeness, says that the derivability relation, being able to prove A in our proof system from assumptions in gamma, is equivalent to logical entailment, to logical consequence, defined semantically in terms of satisfiability in structures, just as we did in lecture 2. So for all gamma, that's a set of formulas and A. I should say that these sets of formulas, we are allowing them to potentially be infinite. Doesn't make much difference for in a proof, you can only use finitely many of them because you've only got finitely many formulas that occur in the proof. But still, we can say gamma A follows as a consequence of gamma, meaning there is a proof from assumptions in gamma of A, and obviously that proof will only use finitely many of the formulas in gamma. But still, sometimes useful to have an infinite set there. Anyway, for all sets of formulas gamma and A, the following are equivalent: T, F, A, E. So firstly, A is provable in our proof system from gamma, and secondly, A is a logical consequence of gamma according to the semantic relation of logical consequence or logical entailment. Now there's a slight mismatch here between how I'm using logical consequence and lecture 2. In lecture 2, I just introduced the relation of logical entailment between sentences. And now, for this statement, it's important that it's also for arbitrary formulas, so formulas that have free variables, because the proof system itself, you can't do proofs using only sentences. When we saw, for example, that we wanted to prove the sentence that was the symmetry of the equality relation, in order to prove that, we needed to have many steps that involved formulas before we formulas that weren't sentences before we added the quantifiers only at the end of the proof. So proofs need to involve formulas as well as sentences. So we're going to need to generalize the logical consequence relation to deal with formulas as well as sentences. Now that's very easy. So we're going to define this relation to be, well, it's simply for all structures M. The only thing we need, so it used to say for sentences for all structures M, if every sentence in gamma is true in M, then A is true in M. We just need to say the same thing, but because we've now got sentences to interpret truth in the structure, we need to give ourselves an environment interpreting the free variables. So we just need to add the clause for all environments, gamma, interpreting variables in M. So if it holds that for all formulas in gamma, all formulas in gamma B are true in the environment M. So earlier I was writing rho up here. Gregor was writing rho down here. Actually, Gregor's one. I'm going to now start writing rho down here. It got too tedious for me. I was getting frustrated in the notes putting it up here. So I'm now going to put the rho down here. Obviously, doesn't matter. But anyway, B, if every formula in gamma is true in M in environment rho, then A is true in M in environment rho. And just because we're going to often have this quantification, I'm going to abbreviate this as gamma is true in environment in structure M in environment rho. Okay, so basically we just need to add the environments, and then it's the same statement that we had in lecture 2. Right. Come on. So the theorem is called soundness and completeness, and I already talked about this in lecture 2. It's got two names because there's what it's saying two statements are equivalent, but there's one name for each direction of the equivalence. So soundness is 1 implies 2. So namely, if we can prove A from gamma, then A is indeed a logical consequence from gamma. And completeness is 2 implies 1. And as I've already said in lecture 2, this is due to Gödel, I think in 1930. The proof I'm going to give is not the same as Gödel's proof. The proof I'm going to give is kind of the modern proof. But in any case, it's a very important and nice result due to Gödel. But for the remainder of this part, I'm going to just, well, if there's a bit of time left, I'll start on completeness, but I just want to tidy up soundness first. So soundness is not a deep result. It's an important result. If soundness were not true, then that would mean we can derive some formulas A, that there's some formula A that we can derive from some set of assumptions gamma that's not a logical consequence of it. That would be a bad thing. The whole point of our proof system is we're supposed to be formulating correct rules of reasoning. If we could derive something that was not a logical consequence, there would be some mistake in our rules of reasoning, and we would want to replace them, or there'd be some mistake in our axiom, in our axioms. So, you know, soundness is important. It says there is no mistake in our axioms and rules of reasoning, but it's actually a very simple result, because to prove soundness, you basically just need to show that the axioms are correct and that the rules of inference preserve logical consequence. The axioms are correct and the rules of inference preserve logical consequence. Now, as I told you at the beginning, in past incarnations of the course, I used to do sequent calculus, and so my notes were, the later notes were all set up for sequent calculus, and last night I was rewriting my lecture notes actually just by hand rather than in LaTeX for this lecture. And when I got to soundness, I thought, well, I can't be bothered to do this now at this time of night. Let's go on and do completeness, because that's the main thing. So I haven't actually prepared the next. So then by the time I finished completeness, I wanted to go to bed. So I didn't go back to establishing, to doing soundness. So I did not prepare the next bit of the lecture. But what we're going to do is, so we want to prove that the axioms, every axiom instance is a logically valid formula. That's a case-by-case basis. Check each one and just inspect the formula, and you'll see that's the case. And we want to show that the rules of inference preserve logical validity. That's absolutely obvious in the case of modus ponens. If A implies B, follows as is a logical consequence of gamma, and A is a logical consequence of gamma, then obviously B is a logical consequence of gamma. So I think the only one that is worth doing is this generalization rule, because that has that little fiddly thing about a free variable, about free variables in it. And it's also a bit surprising in the sense that you're establishing a universal quantifier on the basis of just a single statement about a single variable, so to speak. So the soundness of the universal quantifier rule is the following lemma. So soundness of generalization. So if A is a logical consequence of gamma and X is not in any of the three variables of any formula in gamma, then for all X A is a logical consequence of gamma. Okay, that's what we're going to. So this is what justifies the generalization rule. So this corresponds exactly to that restriction we had on the generalization rule, that we cannot apply it if x occurs as a free variable in one of the assumptions we've used in the proof. Okay. So proof. So suppose that A is a logical consequence of gamma. We want to prove, so RTP, we're required to prove that rule XA holds as a logical consequence of gamma. So how do we prove that? Well, we want to prove that for any structure in any environment, any structure M and any environment rho, that such that all the formulas in gamma are true, then rule XA is true. So consider any structure M and environment and rho such that all the formulas in gamma are true in environment rho and are true in structure M under environment rho. So we want to prove that rule XA is true in structure M under environment rho. And what this means is that for any element little a of our structure, the formula A is going to be true if we modify the environment rho by assigning the variable x the value little a. So consider any element little a in the underlying set of the structure M. So then it holds that if we consider the modified environment where we assign x the value of little a, and otherwise all other variables get the same value that they had under the environment gamma, the formulas in gamma are still true because they do not contain the variable x. The variable x does not occur free, and therefore the interpretation of those formulas in the structure M is independent of the value that the environment assigns to the variable x. So because we've assumed that all the formulas in gamma are true in M under environment rho, and x is not in the free variables of the gamma. So because of this, by the logical consequence, so since rule XA, so since A is a logical consequence of gamma, it holds that A is true in the structure M under the environment rho, where we've assigned little a. So the formula capital A, sorry, it's getting a bit messy down here. So in the environment rho, where we assign little a to the variable x, the formula capital A is true. And we've shown that this is true for every value little a in the underlying set of the structure M, and that's the same thing as saying that rule XA is true in the environment rho, just by the definition of satisfaction for the universal quantifier. So since this is true for any little a in the, let's see, for all, just to make it patently clear, for all little a in this structure M, this shows this is just the definition of satisfaction under environment rho for the formula for rule XA, which is what we wanted to show. Okay, so hopefully you can see from that why the free variable restriction is needed in the generalization rule and how the generalization rule works. Well, it's 3 minutes to, so I really think the best thing to do is stop now, and we'll start again at 12 minutes past. And the last hour is going to be an outline of the proof of completeness, which, as I say, is the most substantial proof that we've going to have considered in this course so far. And a really important result. Right, I'm going to pause the recording. Right, so the aim of this whole hour, so it's going to be the first really substantial proof in the course. So to prove completeness, which is if A really is a logical consequence of some formulas gamma, then our proof system is sufficiently good that we can always find a proof of A following from assumptions in gamma. It's quite a remarkable result. To prove it in this form would be a bit tricky. I mean, you know, if you were going to prove it directly, well, you would assume that you've got a logical consequence, and then you need to come up with a proof, and that's going to be quite a difficult thing to do. So we're actually going to transform this statement into something else, and we're going to prove essentially prove the contrapositive, but we're going to prove the contrapositive in a different form using some different useful and a very important terminology for logic. So we say a set of formulas gamma is consistent if from that set of formulas we can't in our proof system, so consistent with respect to our proof system, if from that set of formulas in the proof system we cannot derive false. We don't want to be able to derive false. From false we could derive anything at all, because we have the theorem in our proof system, bottom in false implies A for any formula A. So a consistent set we can't derive false. We say that gamma is, there's going to be a corresponding semantic notion, which is the notion of a set of formulas being satisfiable. A set of formulas is satisfiable if we can find some structure in which those formulas are true. Because we've got formulas that might have free variables, finding a structure to make the formulas true also entails finding an environment. So it's satisfiable if there exists a structure M and environment rho such that every formula in gamma is true in M under environment rho. Sorry, we're using that notation. Okay. And by soundness, we're going to make an observation. By soundness, we have if a set of formulas is satisfiable, then it is consistent. So any satisfiable gamma is consistent. And this is almost immediate from the definition. Well, from the definitions, there are two definitions, satisfiable and consistent here. So let's just observe why this is the case. We'll put this in blue. So suppose gamma is satisfiable, and suppose for contradiction that it's not consistent. So in other words, we can prove false from the formulas in gamma. So then, by soundness, false is a logical consequence of the formulas in gamma. But this clearly contradicts that gamma is satisfiable, because this says that for all models and for all structures and environments in which all the formulas in gamma are true, false is true, false is never true. So basically this says there are no structures and environments in which all the formulas in gamma hold. But that's an exact contradiction of gamma being satisfiable. So this contradicts, it's immediate from the definition, this contradicts that gamma is satisfiable. So any satisfiable gamma is consistent. What about the converse? Is any consistent gamma satisfiable? Indeed, that's the case. And unsurprisingly, perhaps, I mean, this direction was related to soundness. The other direction turns out to be equivalent to completeness. And this is what we're going to prove. And in proving that, we will prove completeness. So we are going to prove the converse of this, which has an important result. So it has a name. So this is called the model existence theorem. And this says, if gamma is consistent, then it is satisfiable. I just want to observe that completeness is a corollary of this. Let's prove that. So the completeness, remember, is if A is provable from gamma, then A is a logical consequence of gamma. And I want to prove that this is a corollary of the model existence theorem. So I want to prove this implication, but obviously we can equivalently prove the contrapositive of it. So I'm going to assume that A is not a consequence of gamma. So suppose A is not a logical consequence of gamma. We want to prove, hang on. Yeah, there's something very wrong here. Has anyone spotted it? Yeah, so this is not completeness, this is soundness. Yeah. The completeness is that if you have semantic entailment, then you can prove that the formula is a logical consequence. Right, good. So I still want to prove this by the contrapositive. So suppose A is not provable from gamma. So then I claim that if we add the negation of A to gamma, that's a consistent set. So we can't prove false from that. Why does this hold? Well, this is a little parenthesis in the argument, if you like. So let's put it in blue in brackets. So we want to prove that this set gamma together with not A is consistent. Suppose that weren't the case. So suppose gamma together with not A were inconsistent. That is, we can prove false from them. So then by the deduction theorem, which I just abbreviate DT, we have that not A implies false is provable from gamma. So i.e., well, this was just the notation for not A. But since we had an earlier result that not A implies A, since not A implies A is a theorem, by modus ponens we get we get that gamma, that A is a consequence of gamma. And if A is a consequence of gamma, then what? Which assumption? Oh, right. Yeah, yes, here. Right, good. So hash means contradiction in put two arrows pointing together. Yes, great. Okay, so we've managed to derive that gamma together with not A is consistent. So by the model existence theorem, which we're proving the corollary of, so by model existence, gamma together with not A is satisfiable. And this implies that gamma together with not A, but false is not, well, that's the same, that's literally the same as saying, if you expand the definition of being a logical consequence, this is the same as saying that gamma together with not A is satisfiable. And so A is not a logical consequence of gamma, because if A were a logical consequence of gamma, then gamma together with not A would not be satisfiable. So you just because we couldn't have a model satisfying this, because as soon as it satisfied gamma, it would satisfy A. It would not satisfy A. And that's what we wanted to prove as required. Okay, sorry, I seem to have gone into a bit of a confused phase, but we came out of it. Anyway, so a little simple result, and we've got that any consistent. So as long as we can prove the model existence theorem, then we have completeness as a consequence. Just give myself a bit more air and right. So the main tool we're going to use, we want to prove the model existence theorem, and we're going to do this in a number of steps. But the main step is the next result, that I'm then going to postpone the proof of it to the end if we have time to do it. But I want to get the main step written out. So, so our main goal now, our goal has become prove model existence. And it's kind of, it's not a proof that you write proof and then you do the proof and you write the end of proof, because it takes a number of steps and a number of subsidiary results. So the whole of the rest of the lecture is going to be proving model existence. So to that end, I'm going to, let's fix a consistent set gamma. And the whole task is to construct a structure and an environment making all the formulas in gamma true. Okay, that's what the task is going to be. So task, construct an M and row such that all the formulas in gamma true in M under environment. And the way we do this is we're going to build a syntactic. Oh no, sorry. I thought something bad had happened, but it hasn't. Well, something bad did happen in that I apparently didn't move the camera. So I should put the camera over there while I'm clearing the board here. So we want to construct a structure in which, and an environment in which all the formulas are true, in gamma are true. And the basic idea here is we're going to construct a structure out of the syntax of the logic. So our elements of the structure are going to be terms from the logic, actually equivalence classes of terms, and we want to be able to define, those are the elements of the structure, and we need to be able to define the interpretation of the function symbols and the predicate symbols on the structure using the syntax of the logic. And in order to do that, the approach we use is we extend the set of formulas gamma, so it's still consistent, that doing a process that we're going to call saturation, where we add formulas to gamma, as many formulas as we can, so that then the structure of the model that we want can be read off from the extended set gamma. So it's going to be a syntactic structure, and we want to know what properties to assign to it. So which predicates to assign true and which predicates to assign false to, and so on. And to do that, we obtain that by extending the set gamma to a richer set, a larger set of formulas, gamma prime, that will contain that information. And this is actually the proof of this next theorem is the main work in the proof of completeness. And this, well, it's actually not a theorem, it's a lemma. So saturation lemma. So there exists a larger set of formulas, gamma prime, containing gamma, satisfying the following. So firstly, gamma prime is consistent, like gamma was. So we maintain consistency. So this is, we'll just call this requirement consistency. Secondly, we want to make gamma prime as large a set of formulas as possible without violating consistency. So to ensure that, we ask that for every formula A, over our signature, every formula A, either A belongs to gamma prime or not A belongs to gamma prime. So we're committing to either A or its negation being true, in a sense, in gamma prime. This is called completeness. Obviously, we can't add both A and not prime to gamma prime, because then we wouldn't have consistency anymore if we had both A and its negation. And thirdly, that if we have a formula, it's not true that for all xa belongs to gamma prime. Now the idea is, so this formula is not true. So the idea is formulas in gamma prime are going to be the formulas that are true in the structure that we construct, our syntactic structure. So if it's not the case that for all xa, that means that there needs to exist an element of the structure for which not A holds. And because our structure is going to consist of terms, we ensure that requirement by making sure that gamma prime contains an instance of not A with some term substituted for X. So whenever we have a negated universal formula in A, then we require that the formula not A with some term T substituted for X also belongs to gamma prime for some term T. We only need one term for which that's true, but there needs to be at least one term such that this negation of A with T substituted for X belongs to gamma prime. So we call this the witnessing property of gamma prime, because it's basically saying that existential quantifiers, a negated universal quantifiers and existential quantifiers are witnessed by terms that show that they fail. Okay, so the saturation lemma requires quite a lot of work for the proof, so I'm going to postpone the proof. So I've proved it in the lecture notes. We will see at the end of the lecture whether there's any time to do any of the proof of this or not. I may just make some remarks about it. And if we prove the saturation lemma, I just want to make an observation from it. So henceforth, let gamma prime be now the saturation, let's say, of gamma given by the lemma, the saturation lemma. And we're going to work with this gamma prime. And I first want to make a simple observation about it. Gamma prime is closed under derivability. So I mean by that, so that's a lemma. If we can prove that formula A follows from gamma prime, then A belongs to gamma prime. So it's a bit similar to the notion of a theory with respect to logical entailment, that a theory is a set of sentences such that if the formula is a logical consequence of that set of sentences, it belongs, if a sentence is a logical consequence of it, it belongs to the set of sentences already. This is similar, but with respect to the derivability relation, the provability relation that we've got. The proof of this is quite straightforward. So suppose that A is derivable from gamma prime, and suppose for contradiction that A does not belong to gamma prime. So if A doesn't belong to gamma prime, by completeness, then the negation of A belongs to gamma prime. So we have the gamma prime, that A is derivable from gamma prime, and if the negation of A belongs to gamma prime, then obviously the negation of A is also derivable from gamma prime because it's just one of the assumptions. But this contradicts the consistency of gamma prime. Okay. Now, gamma prime is closed under logical consequence. Oh. Well, I'm sorry for the people on Zoom. You can always shout, although maybe just the speaker doesn't work because no one's ever shouted so far. The whole extent of this course, no one's ever shouted on Zoom or even spoken quietly. So the camera was in the wrong place, but now I shall now put it in the right place while I clear the next board. So basically, we've done the preparatory work that we need. We've constructed this saturated set of formulas, gamma prime, and we're now going to read off the structure of them. So we want to construct a structure M, an environment rho, and we're going to read this off from the set of formulas gamma prime. basically the underlying set of the structure is going to be the set of terms, the syntactic structure, but it's going to be equivalence classes of terms by an equivalence relation. And what is the equivalence relation? Well, it's the natural one. It's the relation of those equalities that hold in gamma prime. So we need to know that that's actually an equivalence relation. So let's define it. So lemma, the relation on terms, where I say two terms t and u, these are terms possibly with variables in. So t is equivalent to u if and only if the formula t equals u belongs to gamma prime, so our saturated set. This is an equivalence relation. Why does this hold? Well, basically because the axioms for an equivalence relation are provable from our axioms for the proof system. We did that. We did one example of that earlier. We did the symmetry example, and then given that, because the set gamma prime is closed under logical consequence. Yes.
So this is an equivalence relation on gamma prime, but also on gamma, just on gamma.
No, it's an equivalence relation on the set of terms. Equivalence relation on the set of terms. We're using gamma prime to define an equivalence relation on the set of all terms. Remember, terms constructed from variables, constants, and function symbols. Over the signal. And now we define a structure M by the underlying set. So the structure is clearly M. The underlying set, ordinary font M, is defined to be the set of terms modulo this equivalence relation. The interpretation of a function symbol in M, well, if it's an arity k function symbol, then we apply it to k element. We need to say how we apply it to k elements of the structure. That's going to be k equivalence classes of terms. And this is defined to be the natural thing, which is we make a term from T1 to Tk. Sorry, we get the terms T1 to Tk, and we make a new term by applying the function symbol f to them, and it's the equivalence class of those. Now, of course, for this to make sense, you need to prove that this definition is respects the equivalence relation. And it does so because you can prove in the proof system that every function symbol, that equality is a congruence relation with respect to every function symbol. So those congruence relation properties of equality then tell us that this definition of the operation of interpreting a term on this quotient set of terms does indeed preserve equivalence classes. I won't go into the details of this. I mean, as you can tell, I mean, as you know from anything you ever do involving equivalence classes, such things are always rather tedious. But anyway, it's important to mention that they are true. And finally, the interpretation of a predicate symbol. So we want to say when a predicate, the interpretation of a predicate symbol is true if applied to an appropriate number of arguments of elements from the structure. So these are equivalence classes of terms. Well, this is simply going to be, so a predicate symbol is either interpreted as true or false. And it's going to be true in the case that the formula P T1 to Tk belongs to gamma prime, and false if that's not the case, which is the same thing as by completeness that the negation of P T1 to Tk belongs to gamma prime. And once again, by congruence properties provable from the axioms, one gets that this definition is independent of the representatives of equivalence classes. So this is the structure M. There's an obvious environment. We want to say an environment maps any variable x to, we want to pick an equivalence class from the structure to map the variable x to. Okay, can anyone guess what it's going to be?
Equivalence class of x.
The equivalence class of x, yeah, it's very good. So the variables are themselves terms. We've got our set is the set of all terms modulo equivalence. So the variable x is an equivalence class. So a variable is simply interpreted by itself. It's the most natural thing in the world. And now we have the main lemma. Well, the first main lemma was the saturation lemma, and the lemma that says that everything works is the following, which is for all formulas A, A is true in this particular structure under this particular environment. So in my notes, I was very I called this like M sub gamma prime and rho sub gamma prime to really emphasize that it was a particular structure that we're constructing rather than using the generic M and rho. But on the board, I want to write as little as possible. But it's very important this is a specific M and a specific rho, the one constructed as above. This holds. Well, let's see how. I mean, it's not the easiest stuff in the world, but is anyone on the ball enough to guess what's going to go on the right-hand side here? So the point of constructing gamma prime was to kind of know what the model is. We want to say, know what the structure is. We've extracted the structure from gamma prime in this way. We want to kind of say that. So can anyone guess this? That it's faithful. So the correct thing here is gamma prime tells us exactly what is true in this structure under this interpretation. So this whole constructing this saturated set exactly allows us to read off a structure that the truth or falsity of properties in this structure under the natural environment is literally read off from just checking to see whether the formula belongs to gamma prime. Right, so it's 1:45, and we're essentially, once we do this, we're done because, so given the lemma, we are done. Because obviously every formula in gamma prime is true in A in this structure and environment, and gamma prime contains the original formulas gamma, so every formula in gamma is true in A. So because by the lemma, we have that all the formulas in the original gamma, which is a subset of gamma prime, are true in the structure M in this particular structure M under the particular environment rho. Right. So we are left with two lemmas that we haven't proved. This one verifying the truth of a formula in a model. The truth of the formula in the structure is really just a matter of whether or not that formula occurs in the saturated set gamma. There's a proof of that in the notes, at least some cases of it. Essentially, it's just by induction on the formula structure of A. So in the case that A is an atomic formula, well, if it's an equality, well, then it's immediate from that's how we're defining the equivalence relation here by whether or not the equality belongs to gamma prime. So it's immediately true for equalities just from the definition of the equivalence relation on the structure. It's immediately true for atomic formulas by the definition here, whether the atomic formula is true if and only if it belongs to gamma prime. So we then just need to deal with complex formulas, so implications and universal quantifications. And in each case, one uses these properties, the completeness property in particular, the completeness and consistency property, to show that this holds. And this is carried out in the lecture notes. So I'm not going to do that. What I want to do is return, and I'm not going to do it in detail, but I want to return to the saturation lemma, which is, I think, the more interesting lemma, and give you a very high-level account of why the saturation lemma holds. So let's keep the saturation lemma on the board. But in general, the proof of the saturation lemma actually needs the axiom of choice. We need, let's write AC to prove saturation lemma. Actually, a weaker statement suffices. That weaker statement is sometimes known as the Boolean prime ideal theorem, or it's equivalent to the existence of non-principal ultrafilters. But anyway, the weaker statement, but there's still quite a bit of the axiom of choice is needed to prove the saturation lemma. This is in general. What does in general mean? Well, let's say what the non-general case that doesn't need the axiom of choice is. We're going to avoid AC by making an assumption. What's the assumption? The assumption is the signature is countable. In other words, there are only countably many, that's finite or countably infinitely many function symbols and predicate symbols. This is not a big restriction. I mean, if one's writing out formulas in the real world, then you're only ever going to be able to use, well, anyway, finitely many symbols. So here we're allowing countably infinitely many symbols. But it does prevent us considering signatures like, for example, our signature for rational linear arithmetic, generalized to allow scalar multiplication by an arbitrary real number R. That would be an example of an uncountable signature. But anyway, so signature is countable just means countably many function symbols and predicate symbols, and all the signatures we've considered on the course have been countable. Given this, if you've got a countable signature, there are only countably many formulas. But actually, before doing that, one needs a little technical assumption. So we assume also countably many new variable symbols, V0, V1, V2, but are not free in gamma. So this is just, in order to get our proof of the saturation lemma to work, we need to, at various points, take a new variable symbol that's nowhere occurred in our construction so far. And because gamma can be an infinite set, it could potentially mention all the variables that we started with. So we need to give ourselves a new collection of a collection of new variable symbols to use in order to effect the construction that's going to follow. So now, working in our countable signature with all the original variables together with our new variables, we've still only got countably many formulas. So there are only countably many formulas. So we can enumerate them. A0, A1, A2, A3. These are all the formulas we have over our countable signature and all the original variables together with our new variables, symbols V0, V1. Although we're just putting them in some long list. If you don't believe me that there are countably many formulas, well, you can think about that for yourself. Later on, we will need to do this in a little bit more detail because when we do Gödel's theorem, we're actually going to need to encode formulas as numbers. And at that point, we're going to have to do some of the details of actually enumerating the formulas. But for the moment, for those of you who've done any constructions in set theory of kind of interesting countable sets, it's not that surprising that there are only countably many formulas. Right, well, we've got 5 minutes left, so I'm just going to give you the bare essentials of this construction here. The temperature, d temperature by time, d time, the derivative seems to be very positive. So it's really amazing. I mean, it's the first day of spring officially, isn't it? So what we do is we construct a sequence of sets, starting at gamma 0, which is simply gamma, our original consistent set of formulas, and extending it to gamma 1, gamma 2, sometimes they may be the same set, and so on. Such that, and we then define our saturated set to be the union over all numbers of gamma n. So the unit that everything that eventually appears in this sequence. And we do this in such a way that we guarantee that this resulting final set is saturated. And I don't have time to do many details, so I think the most interesting thing is how one goes from gamma n to gamma n plus 1. So given gamma n, what we do is we consider the formula an, and we check. So if we can consistently add an to gamma n, then gamma n plus 1 is gamma n union an. Otherwise, gamma n plus 1 is gamma n union not an. And by using a consequence of the deduction theorem, one can prove that if it's not consistent to add an to gamma n, then it is consistent to add not an. So one of those two, we are guaranteed that we get a consistent extension here. And that's almost all there is to it, except there's a little fiddly bit. So a little fiddly bit, let's do it in green. except if the formula B and the formula B, which is either, so this is a notation for either AN or not AN, we are adding is of the form it's not true for all X C. So if it's of this particular form and we're adding it to gamma, to our gamma n plus 1, in this case, we define gamma n plus 1 to be gamma n together with B, so which is the AN or not AN that we added. So that's together with for all XC, together with not true C for V sub K, for VK substituted for X, for some variable K not 3 in gamma n union B. And the point here is, whenever we add the negation of a universal quantifier, we make sure that we add, so that's like saying an existential quantification that there exists some X such that not C holds. We make sure that we add a witness to it. And we can always consistently add a witness using a new fresh variable, because if that made things inconsistent, an application of generalization would show us that actually adding B to gamma n would have been inconsistent. So if it's consistent to add B to gamma n, it's also consistent to add this. By generalization rule in logic, I mean, one needs to work it out, but it's also consistent to add this witness. And by this construction, every formula or its negation is added at some stage, so we get completeness. It's consistent at every stage, and therefore it's consistent overall, because any proof of false would only use finitely many formulas. So if an inconsistency arose at the infinite stage, it would have arisen at some finite stage. And lastly, the witnessing property is satisfied because of this last fiddly bit of the construction. And that basically is a high-level overview of the proof of completeness. More details will be in the handwritten notes that I will publish just as soon as I've tidied them up a little bit. I'm afraid for this week, I might put a little bit in the LaTeX notes, but there isn't really going to be a LaTeX companion to this week's lecture, because I just simply, I mean, having prepared the material in handwritten, I don't have time to write it up in LaTeX. So I'm sorry about that. Okay, we now have the proof system and completeness, and next week we're going to start applying it to interesting applications. Right, so that's everything for today. I shall stop the recording.